First section of our gas law chapter is going to be about gas pressure. And we'll talk about pressure equals force over area, the units for measuring pressure, and how to measure it with a manometer. So the formula we use for pressure is pressure equals force over area. So this is force, and the units for that are the Newton, which is broken down further into kilogram meters per second squared. And over here we've got area, which we measure in meters squared. And if we use newtons over meters squared, we end up with a unit called pascals, the standard unit for measuring pressure. So there's our formula, and we can think about force over area as a little area over here, maybe on the ground, and then we have a force represented by an arrow. So this force over this area gives a certain amount of pressure. Now the variables in an equation are related, and we can relate them by indicating whether one of them is proportional to the other one. So I want to be really clear about what that means here at the beginning. So pressure and force are on opposite sides of the equal sign, but they're both on the top in the numerator. And so we can say that they are directly proportional. And we use this little symbol that looks like an alpha or a fish to indicate that. So this symbol means P and F are directly proportional. So if variables are directly proportional, that means that they move in the same direction. So if we increase one of the variables, that means that the other variable is going to do the same thing. It's also going to increase. So if we want to draw a picture of that, if the force gets larger, so here's our box again. So the area is going to be constant. If we increase the force, so we make a bigger arrow on our picture, a little wider, a little fatter. So if we use a larger force and the area is constant, that is going to result in a larger pressure. So those two variables move together in the same direction. And so now let's talk about pressure versus area. So pressure and area are on opposite sides of the equal sign, but one is on the numerator and one is in the denominator. And so that means that these two are inversely proportional. And there isn't a symbol for inversely proportional. So what we say instead is the pressure is directly proportional to 1 over the area. So this means they're indirectly proportional. And if two units are indirectly proportional, then they react in opposite ways. So if we were to increase the area, that means the pressure would do the opposite. The pressure would decrease. So if I were to make my area really big this time, larger area, and we'll put that same amount of force as in the first situation. This is supposed to be the same size as the first picture. So force equals constant. Force equals constant, and the area has increased. That causes the pressure to decrease. So this is how we're going to talk about how variables are related in a formula. So this force that's part of the that's part of the formula for pressure can be exerted by any phase of matter. So it can be exerted by a solid, a liquid, or a gas. So this might have been some of you over the weekend on moving day, carrying heavy stuff, carrying things. Those are solids. The solid is exerting a force on you. If you've ever been diving and worn some big flippers, hopefully you can tell what those are, and used a snorkel and carried a tank on your back, you're underneath a large amount of liquid, the water in the ocean, and the water in the ocean exerts a force on your body when you're underneath it. Oh, I forgot arms. Hold on. There. Now we have some disproportionate arms. And if you're just hanging out watching the lecture somewhere on the planet Earth, let's say right here, you are still feeling the pressure. You're feeling the pressure of a gas. You're feeling the pressure of all of the air that's above you in the atmosphere weighing down on top of you. That column of air up to the edge of the atmosphere is 50 kilometers tall. And you must think to yourself, that is super heavy to feel the force of all that air weighing down on top of me. But the reason we don't notice is because our bodies have evolved to deal with that kind of pressure and to push back from the inside of our body at the same pressure. So we don't actually feel this pressure because we've evolved not to feel it, but I can guarantee that you feel the pressure of heavy things on your back or of being underneath the water. When we talk about pressure, we need to talk about it with units. So as we mentioned above, the SI unit for pressure is the Pascal. But in some situations, we prefer to use other units. So my preferred unit is the atmosphere. And 1 atmosphere represents the pressure at sea level. So here's some other ones. So 1 atmosphere, which is the pressure at sea level, is equal to 101,325 pascals. It's equal to 1.01325 bars, which is a different unit. It's equal to 14.7 psi, which American systems often use to measure tire pressure. It's equal to 760 torr, which many lab instruments use. And it's equal to 760 millimeters of mercury, which is a unit of pressure that's very easy to physically measure. So these are all different units of pressure that you might encounter in your life or in practice problems, and you should be able to use these conversions to convert between them. Okay, let's move on to the next section. We want to measure pressure, we need to be able to use an instrument, and the instrument of choice for measuring the pressure of a gas in a flask is called a manometer. So the different parts of this are some sort of a flask with a gas in it at one end. The other end, in this case, is open, so this is called an open-end manometer. And in the middle, there's a U-shaped bend, and that's filled with a liquid, usually a pretty dense liquid, like mercury. Mercury is one of the densest liquids that exists at room temperature. This is going to be our liquid. And what we're interested in is the difference in height of the 2 ends of the liquid. So here's one end, here's the other end, there's the difference. So that difference is called H, the height difference. And that height difference tells us about the difference in pressure between the 2 ends. At one end, on this end that's open, the liquid level is being pushed down by the air outside from the atmosphere. So there's a force on this side. And on the left side is the pressure that comes from the force of the gas, pushing down on the left side of the mercury column. So this is going to be the gas pressure. This is going to be the atmospheric pressure. And so what we want to know is we want to figure out which side is pushing harder and solve for the pressure of a gas. So we can see in this picture that the liquid level is lower on the open side. So that means that the pressure of the atmosphere is greater than the pressure of the gas, because the atmosphere on this side is pushing the liquid level down more than the gas is pushing down. The atmosphere is pushing harder. So if the atmosphere is pushing harder, that means that should be the larger number. So we can convert between these two pressures using the height difference of the liquid. So the pressure of the atmosphere minus the height level of the liquid gives us the pressure of the gas. And we could also have the opposite. We could also have the pressure of the gas be stronger. So if we put the open side liquid level up a bit higher, so we've got like right here and right here is our height difference. So the pressure of the atmosphere is going to be a little smaller this time. And then for our gas over here in red, it's going to be pushing down a little bit more. So now we have the opposite case. So now the liquid level is lower on the gas side. So the gas is pushing down harder than the atmosphere. The pressure of the gas is greater than the pressure of the atmosphere. So that means we need to take the pressure of the atmosphere and add the height to get a larger number for the gas. So let's do a quick example calculation to make sure we're all on the same page for how to use those formulas. So let's take that first figure up above, and let's see that let's say it was measured at sea level. We'll say that the height of the column, the height difference is 13.7 centimeters of mercury. And we'll try and find that gas pressure. So in the first picture, we can see that the atmosphere is pushing down harder than the gas. So the atmosphere number is going to be bigger, so we need to subtract the height from the atmosphere number. So larger atmosphere minus height gives us smaller gas pressure. And what we need to do is we need to find the number for sea level, and we need to make sure that the sea level and the height numbers are in the same units. So sea level means that it's at 1 atmosphere. But I can see that the height was measured in centimeters of mercury. So I'm going to change this unit using dimensional analysis, which should be a review from your previous chemistry courses. So I'll put the unit that I have on the bottom and the unit that I want on the top. I'm going to convert from atmospheres to millimeters of mercury. Excuse me, that conversion is from 760 to 1. So that will give me the pressure atmosphere in millimeters of mercury. And then I'm going to subtract the height of the column, which is 13.7 centimeters of mercury. And centimeters of mercury is okay, but the standard unit is millimeters of mercury, so I'm going to convert mine to that, since I already converted the left one, that unit. So we'll put the unit we have on the bottom, the unit we want on the top. The conversion is 10 to 1. And so that puts us in millimeters of mercury. So we've got 760 millimeters of mercury minus 137 should give us 623 millimeters of mercury for our gas pressure. And if we go back and do the bullshit test to make sure that we're doing this correctly, we saw from the picture the atmospheric pressure should be larger than the gas pressure. So our atmospheric pressure was 760 and our gas pressure is 623. So that is indeed less, and that is how we read a manometer.